Screens. They display technology that is found almost everywhere in our world today. From the laptop used to do your schoolwork, to your beloved phone, and even your Apple Watch. Screens have become a vital part of our world today, and I'm going to look into, literally, how different types of displays and touchscreens work and explain the physics behind them. To begin with, we have the cathode ray tube, also called a CRT, which was invented in 1897 by German scientist Carl Ferdinand Braun. A CRT is a glass vacuum tube that has a positive terminal called an anode and a negative terminal called a cathode. When you connect a battery to each terminal at a specific voltage and pressurize the tube at a very low pressure using a vacuum to minimize collisions between electrons and gas molecules, a ray is shot out of the cathode. This machine allowed scientists to conclude that this ray was not only charged, but contained negatively charged atoms, now called electrons. They discovered this because the ray was affected by electric fields and magnetic fields. To put it simply, the naturally occurring electrons in the cathode are collected by the anode due to the electrical current created by the voltage. Now that we know how a CRT works, we can go over how some of the first ever screens were made. First, the glass tube is coated with a phosphorescent material called phosphor, which would glow when struck by electrons. Next, three different colored CRT setups, hence why the old TVs were so big and heavy, would be shot simultaneously, many times per second, partnered with coils of wire that would generate a magnetic field which could control where the electron rays would go. Overall, this would allow the electron rays to sweep across the screen and overall create an image. And boom, now you can watch your favorite cartoon. To dig a little deeper into how these deflecting coils work, we can look at the formula for the magnetic field of a loop. B equals mu naught I over 2R. In this formula, we can see that I is proportional to the strength of magnetic field B, so to change the angle at which the electron beams strike the screen, we must increase the current I. And in turn, our electron beam becomes more affected by the stronger magnetic field. So you might be wondering why only three colored rays are being used. Well, this is because with the colors red, green, and blue, we can mix and combine the three to create any other color. For example, red and blue make purple, red and green make yellow, and so on and so forth. This concept will be brought up again later with the use of pixels. Fast forward 60 years to 1962, and we have the LED, developed by Nick Holoniak Jr., which stands for Light Emitting Diode. The construction of an LED is the same as a PN junction diode is. Some other people have gone over the PN junction, but for a quick recap, when you connect a voltage source, free electrons gain enough energy to cross the PN junction and recombine with the holes in the P region. When the electrons cross over, they release energy. Usually in diodes made of silicone, this energy is released as heat. But in LEDs, which use semiconductor materials like gallium arsenide phosphide, photons are created and energy is released as light. The only limiting factor of LEDs was that only one color per diode could be created. As I just mentioned, this was due to the material. However, the wavelength is another important factor which determines the color produced. In this table, we can see the currently used voltages, wavelengths, and materials used to create certain colors. This table was found using these formulas. Energy equals voltage times charge, and energy equals Planck's constant times the speed of light divided by the wavelength of the photon. And from that, we can get this formula. Scientists then use this formula, along with different materials, to discover what voltages and what wavelengths created what specific colors they were looking for. From this, LEDs were great for things like alarm clocks and traffic lights because they only required one color to be created. A simple array of LED diodes could be used to create an image. However, this was limiting to display technologies like TVs. So, 6 years later, in 1968, the liquid crystal display was created. LCDs are most commonly found in monitors, cameras, and displays within cars. These are far more complex than the early on LED displays, but let's get into it. To begin with, there are 6 total layers in an LCD display. You have your fluorescent lighting, a vertical polarizer sheet, followed by your optical sheet, which contains the liquid crystals. You have a horizontal polarizer sheet, your color filter, and then your typical glass panel on the outside. Your light source, which consists of numerous fluorescent lights, shoots light waves, which consist of both magnetic and electric fields that are perpendicular to the direction it is shot. Keep in mind that both these fields are present in all directions. So for simplicity's sake, in these pictures, just the electric fields are shown. So as we reach the first vertical polarizer, as the light waves reach the first vertical polarizer, these things are made of plastic and they're covered in iodine, which create the polarizing effect. The light waves pass through, but only the vertical electrical field lines remain. We then get to our optical sheet, which consists of the liquid crystals, and they manipulate the course of the light waves. I'm not going to dig too deep into it, but these liquid crystals are usually found in twisted state, as you can see here. So the entering vertical lines are rotated as they pass through and become horizontal, so they can pass through the horizontal polarizer and then strike the color filter, produce whatever color that may be. However, in the case that we don't want to color, for example, say red, we can connect a voltage to the liquid crystals and alter the voltage to rotate them and control how much of the electric field passes through and reaches the next polarizing sheet. This phenomenon is called the twisted nematic effect, and if we look at this formula, it's a little crazy, but what's important to us is that delta, which is the phase difference that the liquid crystals induce, which is essentially how much they rotate, is proportional to the voltage. So the key here for us in this class is that the increase in voltage is going to rotate the liquid crystals so they are back to their original parallel state. So up here you can see if we want cyan, for example, which is just blue and green, we alter the liquid crystals in the red subpixel, so increase the voltage here. So that rotates these light waves so the electric field lines don't pass through, hitting the red color filter, which leaves you with just blue and green on this side, and cyan is produced in the pixel. Alright, so that was probably a lot to digest there, but when you put a bunch of these together, you get a basic LCD. And each square on the right here, as I mentioned, is called a pixel, consisting of 3 subpixels. This picture isn't the best, but you can imagine that the backlighting here consists of a bunch of fluorescent lights. They're usually horizontal. Alright, so a pixel, as I just mentioned, is a square consisting of 3 subpixels, red, green, and blue. And as mentioned earlier, with these 3 colors, any single pixel could create any wanted color just by manipulating how much red, green, or blue is shown. On the right here, you can see some common resolutions for TVs and monitors, and the resolution is just the number of pixels on any given screen. The most common is 1920 by 1080, and that comes around to about 2,070,000 pixels. So you get an idea of like how many pixels go into a screen and just how small they are. New LED displays. The only difference functionally between an LED and an LCD display is, like how I mentioned earlier, the LCD uses fluorescent backlighting. The LED uses individual LED backlights for each pixel. So both still use liquid crystals, but the LED is slightly more power efficient and they have a longer lifespan. Moving on to OLEDs, also known as organic light emitting diodes. OLED displays are slightly different from LED and LCD displays in that they don't have any backlighting or liquid crystals within them. Rather, they have individually lit pixels that change brightness based on the current that passes through them. Here you can see each pixel contains an emissive and conductive layer smashed in between a cathode and an anode, which creates a circuit. Each subpixel within the pixels contain different specific organic emissive layers, which creates color through a similar process like LEDs. The same electron-hole combinations are constantly occurring, which emit different wavelengths, and said wavelengths, along with the type of organic material, determine the color produced, just like LEDs. Included this graph here, which represents the sort of wear and tear over time. This obviously isn't going to be super accurate to everyone, but you can see here that the max brightness is going to go down obviously, but the wear and tear is due to the actual conductivity of these materials within each pixel. As they're used over time, the conductivity goes down, meaning less current is able to be passed through the material, meaning they are less bright. QLEDs. So the Q in QLED stands for quantum dot, and essentially there's just a thin film placed over your typical LED display, and these quantum dots are extremely, extremely small semiconductor particles that make your colors more colorful and bright. There isn't much else to it. People mainly just see it as a money grab by these big brands like Samsung, who they smack QLED on the box and convince people that there's some crazy new tech in their TVs, but to me, there is no major benefit to spending a crazy amount of money just to watch some TV. Resistive touchscreens, also known as your annoying Taco Bell kiosk screens. These screens have two main layers. You have your plastic outside layer and your glass inside layer. All of this on top of your typical display. Inside is this conductive material that is plastered on called ITO. It stands for indium tin oxide. So what happens when you press onto this plastic outside layer, it touches the inside glass layer, creating a circuit. So the processor within the screen knows it's being touched. But how does it know where on the screen? Well, the ITO is applied usually in a grid pattern, so your screen knows precisely when and where it's being touched, and when the circuit is complete at that point. So next time you go to order your Crunchwrap Supreme, even though you told yourself you aren't going to have it anymore, you can visualize a little grid on the screen because you know how the screen works. I need to be better with my money. Anyways, capacitive touch screens, aka the ones you find on your phone. These are slightly more intricate than your Taco Bell kiosk. They contain 4 layers, 2 dedicated to ITO, an insulator in between the 2, and then a glass panel, which you don't see here, but usually that just plays the role of protection. The bottom ITO gets a bunch of electrons that create a negative electric field because it's trapped by the insulator. In turn, the top ITO gets a bunch of positive charges. This creates what we know as a capacitor. And there's just a bunch of stored charge just hanging out. So, when you touch something that conducts electricity, like your finger, or in this case, a hot dog, the electric field changes and charges are passed on to whatever is touched. From there, the processor within your phone senses the change in charge at that certain point and clicks whatever that may be. The main point to be made here is that whatever touches the screen has to be conductive. That is why when you touch your screen with gloves, well, nothing happens, because gloves aren't usually made of a conductive material. Regarding the future for screens and displays, we have the micro LED. Creating micro LEDs involves very advanced nanofabrication techniques to produce these LEDs that are less than 100 micrometers in size. The reason these micro LEDs haven't gone into major production yet is because it is so difficult to manufacture a small LED in a power efficient and cost reliable way. On the bottom here is a little representation of how many micrometers are in a single millimeter, and on top is a close enough to correct scaling so you can see or can't see just how small these micro LEDs really are. Another major issue is micro LEDs still generate heat, and their small size makes heat dissipation very challenging. So efficient thermal pathways are crucial to maintaining performance and longevity, and given it is already hard to make these tiny LEDs themselves, finding a way to keep them cool efficiently is going to be an ongoing issue. The Sphere in Las Vegas, which you probably have seen before, uses micro LED technology, and it is evident that it offers superior brightness, contrast, and color accuracy compared to your traditional LED or OLED display. The benefit to having extremely small LEDs is the ability to create seamless curved displays while maintaining a high resolution, as you can see. You can imagine that there are hundreds of panels that make the Sphere that each house thousands of micro LEDs, and these panels are placed in a continuous curvature to create the round spherical appearance. But as you would imagine, this takes an unbelievable amount of energy to power, not only the inside screens but the outside screens as well, which is around 28 megawatts. Doesn't sound too bad, but that is enough to power 21,000 homes. One possibility I found for the future of screens is the use of plasmons, which is the quantum of plasma oscillation. Where in physics this stems from, I have no clue. But these screens would harness surface plasmons, which are collective oscillations of electrons, and these are smaller than light waves. And this would allow for the creation of pixels and subpixels that are smaller than the wavelength of visible light, which significantly increases the resolution display. Essentially, the pixels I showed you earlier would become even smaller and far more efficient visually. Well, that wraps up the topic of screens. Hopefully you learned something new. Thank you for watching.